He's a Marie Curie Research Fellow and a faculty member at the university called Pompeu Fabra in Barcelona. His work manages to bring together several fascinating and traditionally distinct areas of research, including mobility, migration, law, public policy, social segregation, citizen science, and disease ecology. And John is uniquely qualified to work at this sort of union of disciplines. He has an undergraduate degree in ecology from Cornell, and then he got a law degree at Cornell. He clerked for a federal judge working on immigration law, and then worked in refugee programs with the UN in the Balkans. Then he returned to grad school and got a PhD in demography from Princeton. I sat next to John in grad school for some of our time together, and I can personally attest to his boundless energy, curiosity, and creativity as a researcher. So I'm really excited to see what he's going to talk to us about today. So please join me in welcoming John Palmer.
Thank you very much. That's the best introduction I've ever received. Thanks a lot for having me here. It's really a huge honor and a huge treat to be able to come. Thanks a lot to Liz, especially for helping set everything up, and Dennis and Danny for all the hospitality. Thank you for coming. So yes, I want to talk today about the relationship between people and disease vector mosquitoes, like this one here, which is tiger mosquito. It is Pictus. And the reason I want to talk about this is because disease vectors have become a really big issue in public health during the past 2 decades. There's been a large increase in dengue, which now affects between something like 100 and almost 400 million people each year. There's been several million cases of chikungunya and Zika over the past several years, and Zika, of course, triggered a major international public health emergency because of its rapid spread and because of its links to neurological issues, including microcephaly. And although malaria has been decreasing in recent years, it still affects enormous numbers of people, something like 200 million cases per year. And all of this exacts an enormous toll on society, and a lot of that toll is focused on the poor. And these are diseases, all of these are diseases that are spread by mosquitoes, by Aedes albopictus, by Aedes aegypti, and by several other mosquitoes that are important vectors. So it's important that we understand the dynamics of this relationship between mosquitoes and people. And what I want to talk about is a basic hypothesis that social inequality and disease vector mosquitoes are in a feedback loop. So disease vector mosquitoes exacerbate problems of social inequality, and social inequality exacerbate problems of disease vector mosquitoes. Depending on what we mean by this and at what scale we're talking about, part of that is fairly well established, but there's part of that hypothesis that's not well established, and there's a lot that we still don't understand, I think. So what I'm going to talk about is what we already know. I'll talk about how we can learn more, and specifically I'll go into a citizen science project that I've been working on for the past 4 years in Barcelona in order to try to get at more fine-grained information about mosquito population densities in conjunction with information about human mobility in order to understand some of these questions better. And then I'm going to talk about what's missing and the future directions that I've been thinking about in this area of work. So to go a little bit deeper into this hypothesis, this is a simplified version, but it's a little bit more complicated than that. So disease vector mosquitoes influence social inequality through the diseases that they transmit. But then social inequality has an effect, I believe, both on the diseases as well as on the mosquitoes. So the feedback loop is a little bit more complex. There's an inner loop between social inequality and diseases. What do we know about this so far, and why does this hypothesis seem reasonable as a starting point? So the route from mosquitoes to disease to inequality is probably the best established part of this whole thing. The World Health Organization, in drawing attention to the problem of vectors worldwide in 2014, stressed that these diseases exact their heaviest toll on the poor. In fact, they justified increasing interventions with respect to vectors, disease vectors, largely because this would also have an effect on reducing poverty and reducing inequality. So the mechanism by which this appears to happen is, first of all, because people with less resources tend to be more exposed to both disease vector mosquitoes and to the diseases themselves. So there's obviously a big difference in terms of your exposure to mosquitoes if you're working in an office with air conditioning and the windows shut, and in comparison to whether if you're working outside, particularly outside during the hours when disease vector mosquitoes are biting. Treatment costs. Getting dengue or chikungunya or Zika may have more or less of an impact on your life, on the rest of your life course, depending on whether you can afford the treatment, whether you have somebody in your family who can give you care, whether you can afford hospital costs. And similarly, it'll have more or less of an effect on your life if you have stable employment and paid sick leave, as opposed to if your entire livelihood depends on your physical labor, because these are diseases that generally knock you out for a relatively large amount of time, and that can have a much greater impact on somebody with less resources, somebody who's at a very precarious position, than it does on somebody who's more wealthy. So that's the basic mechanism by which mosquitoes transmitting disease exacerbate problems of inequality. The other direction is the part that's less well established, but there is already literature on both paths of that other direction. So the first path is inequality to the diseases themselves. There is one explanation, which is that the size of the exposed human population when there's greater inequality, for the same reason I just mentioned about greater exposure, is increased, and therefore there's more hosts for the disease to be passed to. But then there's a more subtle and I think more interesting possibility, which is that there's actually stability in metapopulations of the diseases themselves as a result of human segregation. And by segregation, I mean not just residential segregation, but activity-space segregation. So the segregation in where people spend time as they go about their daily activities. This is something that was suggested in a very interesting paper by Adams and Kaplan from 2009. And they sort of
Can
turned...
you just say what
Sure.
metapopulation stability means?
Okay, so the idea is that if you have a population that is at risk of extinction, so there's always this risk that you're going to cycle down towards extinction, if it's one homogeneous population, that the probability of that extinction would be much larger than if you have separate subpopulations with some transfer between them, but barriers between them as well. So that way, if one subpopulation becomes extinct, it may be resupplied by members of another subpopulation. And so in the aggregate, that metapopulation of these distinct subpopulations tends to be more stable. So that's a theory from ecology. It's well established for certain populations, and it's been explored in the context of epidemiology for various diseases. So the Adams and Kaplan paper takes that idea, and they look at they sort of turn the idea of vectors and hosts on their head, and they think about what if disease vector mosquitoes are largely staying still. And in fact, in the case of the vectors for chikungunya, dengue, and Zika, they don't fly very far. They fly several hundred meters in the course of their entire life. So these mosquitoes tend not to travel very much. And what if we think about it as humans who are passing the diseases back to the mosquito populations? So the disease stays around because these distinct subpopulations of mosquitoes keep getting reinfected by the humans who are traveling to them. And you can think about this a little bit in terms of like one of these space-time accordion diagrams, where here the vertical axis would be time. These are the paths of two different people going about their daily activities. And when we think about things in this three-dimensional space-time cube, this is two-dimensional space here. So we tend to see these columns where people live and columns where people work, and then movement in between those places, and sometimes little additional paths. You can imagine, so these are two people moving around during the course of their day. This cylinder in the middle is a distinct population of some disease vector mosquito that doesn't move very much, and that concentrates and bites during 2 times a day, in the morning and the afternoon. So you could have a connection between these people because one person passes through this area and spends some amount of time in contact with those mosquitoes in the morning and goes about their business, and the other person does so in the afternoon or late. Or in fact, it could be separated by several days. So this is the idea in the Kaplan paper. So you have these largely static mosquito populations with people moving through them. When they model the dynamics of a sort of generic, they're thinking of one of these 3 diseases, of dengue, chikungunya, or Zika, as this disease passes through the 2 populations. The classical theory of metapopulations and also the deterministic models suggest that the less mixing that there is, in fact, if there's just an intermediate level of mixing between people, so you imagine everybody has some home location, and then they also go to they visit some distinct mosquito population every day. The less mixing there is between the people, so the more distinct the paths are, the more separation there is between the human activity spaces, the more the disease can be expected to persist. That's their deterministic model. When they actually run it as a stochastic model, they don't find that. They find that, in fact, more mixing tends to lead to greater persistence of the disease. So it's not entirely clear if that's a matter of the parameters that they used, or perhaps this is suggesting that metapopulation theory doesn't actually hold a lot for understanding the stability of disease, mosquito-borne diseases in this context. But the idea, I think, is very interesting and very useful for thinking about this further. The second part of the route here is inequality affecting the mosquitoes themselves. So not only could inequality boost the disease, inequality could also boost populations of mosquitoes. And there's three basic mechanisms by which this might happen. It might happen because neighborhood disorder tends to be associated with greater breeding sites for these mosquitoes. So the mosquitoes in question here breed in small containers of water. Those small containers of water can be created if there's trash on the street and there's rain and the trash is not picked up. So, and there's at this point numerous empirical studies showing a strong relationship between neighborhood disorder or poverty and prevalence of tiger mosquitoes. It's also possible that increased water inputs from humans, which would be associated often with more wealthy areas, also create greater breeding sites. And this is something we see when we start modeling mosquito prevalence and looking at weather data, is that the relationship between mosquitoes and rain is not at all straightforward. Sometimes more rain will produce more breeding sites, sometimes less rain will mean that there's more people putting water into the environment themselves, filling up flower pots, etc., and that's creating breeding sites. So inequality will create greater areas of poverty and greater areas of wealth. And the combined effect of those two things, or those things on their own, individually, should have a role in boosting mosquito populations, but their combined effect should also have a role. And one way that might occur would be if vector control strategies target only one or the other of these types of breeding sites. And in fact, there's an interesting paper by Unlu from 2011, which suggests, first of all, that there's this relationship that we've seen elsewhere between poverty and mosquito populations, but also that in the case of Singapore, one reason why vector control strategies had failed was because they were targeting poor areas and the mosquitoes were continuing to breed in wealthy areas where there was a lot of lawn care, a lot of water being put into the environment, and those mosquitoes, as soon as the vector control operations were finished in poor neighborhoods, those mosquitoes would simply recolonize the poor neighborhoods. So that's a way in which those two things combined should have a greater overall effect and create greater resilience of the mosquito populations. Okay, so that's a short summary of what we know so far. How can we learn more? And one of the big obstacles to learning more, particularly about this pathway from mosquitoes back, from inequality back to mosquitoes, is that we don't have a lot of information on mosquito prevalence. We don't have a lot of information on actually how mosquito populations are distributed across space and across time. One of the main obstacles that we have is the traditional methods of mosquito surveillance rely on oviposition traps. You go out and you put a small bucket of water that has a little piece of wood, the mosquito lays their egg, and you go back in 2 weeks and you check the trap. That has to be done by entomologists. And so scaling up oviposition traps tends to be expensive. The more traps you need to put out, the more money it's going to cost, the more time, etc. Our experience in Spain, so my work on this question started with data from oviposition traps. We started modeling this data that was from 2009 to 2011. It stopped in 2011 because the governments ran out of money. So, and it was also very limited in terms of the space it was covering. And if you compare that data to the actual the extent of the range of these mosquitoes in Spain, the tiger mosquito is an invasive species, it's moving very fast and it's skipping past the areas in which oviposition traps are being put much faster than the mosquito control authorities can keep up. That's particularly the case because the mosquito control authorities there, as often is the case in other countries, they're organized at the municipality level. So there's also sort of an administrative institutional problem, which is that you have all these very small scale institutions with not very much money putting out ovi traps, with very limited ability to coordinate with each other because of resource constraints, and you have this mosquito that's not constrained by any of those things. So that has been our main obstacle. The alternative that we started thinking about was, so this by the way, this is a map of essentially all of the OV traps in Spain during 2014 and 2015. So you can see that they were placed along the coast and the places where mosquitoes were expected. What we started thinking about, and others around the world have also started thinking about, is what if you could take the actual hosts, the people that are being bitten by the mosquitoes, and you could network those people together and get them to serve as the OV traps, as the sort of sentinels for when mosquito presence was occurring. And this is one of the basic ideas behind networked citizen science. You empower people to be scientists, you empower people to conduct research. And there's different philosophies of citizen science, different ways that one can think about what the role of the individual citizen scientists are. At the very sort of low end of the scale is this idea of, okay, people can be sensors, people can go out and collect information, they can collect data, and that can be useful. Citizen science then moves all the way up to let people also be part of the decision-making process about what research questions are going to be asked, to let people be involved in analyzing, non-professional scientists be involved in analyzing data, publishing papers, etc. So we decided to start on this idea of citizen science by putting together a project in Spain that would allow people to very easily report when they saw tiger mosquitoes. We created a mobile phone application that had a very simple taxonomic key and a nice collection of photographs so that people could easily identify tiger mosquitoes. In Spain, it's really only the tiger mosquitoes is what we're concerned with at this stage. We don't yet have yellow fever mosquitoes. So the idea was we give people this tool. We facilitate their ability to identify and report tiger mosquitoes. We then collect all that data, we share it back with the public, and we want to analyze it and learn something from it. One of the main concerns that we had was, all right, why should we think that this is going to be accurate? We can do a great job of telling people how to identify mosquitoes, but maybe people are just going to use this to play games. We don't really have a good way of controlling the quality of the data that we're getting. The second big concern that we had with this approach was, how do we know where people are looking? How do we know that we're not just going to get data from the areas where people happen to have smartphones and are interested, and we're not going to get any data from the areas where people don't have smartphones or don't have time to participate in a study like this? And in fact, if we really care about social inequality, that should be a major red flag in terms of whether this is a data collection technique that could be useful. So the strategy that we adopted to deal with that was to actually measure or estimate sampling effort using background tracking. Since 2014, we've ended up with about 38,000 participants cumulatively. We don't have 38,000 participating at any one moment in time. We usually have several thousand depending on how many mosquitoes are biting. And we've collected over 11,000 reports. These maps with the yellow here show the background tracks of our participants since the beginning of the project. This is just a close-up of Spain, so you can see the comparison with basically where sampling effort is being placed by citizen scientists as opposed to OV traps, and then this is the entire world.
The background track is?
So I'm sorry, the background tracking is this, so that the mobile phone application gives the person the option of having their phone at five random times a day take their location, to determine their location based on satellites, based on the network data, and anonymize that and send it to our server so that we end up with information about where the people who are using the app were located. It's rough information. It's rough information for several reasons. First, primarily because we're worried about privacy. We didn't want to be in the background collecting the exact locations where people were going. And people themselves may switch the thing off. So we don't get it for everybody. And in order to ensure that the data is anonymized, we don't get exact locations. What we did was we predefined a grid of 0.05 by 0.05 latitude and longitude. The phone determines its own location, and then it figures out what grid cell it's in, and it passes the server the ID of that grid cell. So all we know is at one of those 5 times a day, there was this many people in that grid cell. And then 0.05 by 0.05 latitude longitude in Spain is approximately 20 square kilometers. Okay. So, and you can actually see if you want to have a. So these are the sampling cells right here. That's compared to the provinces of Spain, the provinces of northeast Spain, and these are the sampling cells if you zoom in on Barcelona. So you get approximately 4 sampling cells for Barcelona, a little bit of a 5th one. For other towns, you get about 1 sampling cell.
Are you going to talk about how you recruited people, or
Sure.
ads, or?
So basically we launched the application and we relied on a combination of social media and traditional media to spread the word and to let people know. In addition, we've spent a lot of time going around to various science festivals, to museums, and doing talks and doing little workshops where people can see how the app works. They can learn about mosquitoes, they can see actual samples, they can see what mosquito larvae look like. So there's been a large part of the project has been this outreach side, and that's partly recruiting, and it's also partly the idea of being involved in letting citizen scientists learn about science and participate in science. So that's been one big chunk of the project. There's also whole other aspect, which is feeding that data back to the public health authorities, which are organized at the mosquito control services at the municipality level, and that involves getting in contact with them individually. So what do we learn from this data? So first of all, leaving the sampling effort part aside, simply as an early warning mechanism, what we find is that the citizen science data has alerted us to the presence of tiger mosquitoes in municipalities that we did not already know they were present in based on the ovi traps. And those municipalities tend to be much farther from the known invasion area. So you have sort of the known area that the municipality, that the ovi traps have detected tiger mosquitoes in. And what we find is that there's this jumpy quality to where tiger mosquitoes are detected next. One reason why these have been detected, these distant ones have been detected more often by citizen science, is that the ovi traps tend, since the assumption is that there's this spreading process, the ovi traps tend to be placed right at the border of the invasion area. And since they're expensive, you don't have a lot of money to then randomly sample a lot of other municipalities.
Is there a chance that people are wrong sometimes about their reports, or is it pretty obvious if you see like?
Yes, so that's
Sorry.
that's a perfect question. So in terms of the early warning part, there's a whole protocol that the municipal and regional and national government in Spain goes through for actually officially deciding the municipality has tiger mosquito presence. And that's only triggered when an entomologist goes to the field and catches tiger mosquitoes. So we have this data from our maps. That then gets sent to an entomologist who goes and places an open trap and confirms there's a tiger mosquito. So for this early warning where you really care about getting it right, somebody goes to the field and double checks. For the other part, we got all these photographs, and one of the nice things is we can send out a message and say, hey, we're really interested, are tiger mosquitoes in your cars? Are they being transported by cars? Is that one of the reasons why there's this jumpy pattern? And people start sending us back pictures of smushed mosquitoes in their car. All of the photographs that come in with the reports are sent through an expert validation process. And so that's that side of being concerned about the quality of the data. So we have a team of entomologists who review the photographs. They have a separate portal to the server, and they simply review photographs as they come in. 3 entomologists review every photograph independently, and they come to an agreement on whether it's probably a tiger mosquito, possibly a tiger mosquito, they're not sure, or probably or possibly something else.
Are these things that look like stripes, is that why it's called the tiger mosquito?
Yes, yes. The tricky part, so it's relatively easy in Spain because this is there's no other mosquito that looks really like that in Spain. The other mosquito that I mentioned in the beginning, the yellow fever mosquito, or Aedes aegypti, looks fairly similar. And in fact, when the Zika emergency was declared, we realized that we were getting data from around the world. We realized we should be covering the yellow fever mosquito as well. And so we changed the taxonomic key to make it possible for people to distinguish between the two. But we had a lot of reservations, particularly the entomologists had a lot of reservations about whether that was going to actually reduce the quality of the data because people are getting confused. But so our strategy has been to go through this expert validation process. So we then take the expert validation information and the sampling effort information, and we use that to model mosquito prevalence. The sampling effort side is actually more complicated than I made it out to be, because what we realized when we started looking at how people actually participated and how they interacted with the app, what we found was that most people, they download the app because they're being bitten by a mosquito, they report the mosquito, and they forget they have the app on their phone. So we did this analysis of participation time And so we looked at the rate with which people withdraw, and you can also simply delete the app from the phone. So what this shows here is first just a histogram of the number of people participating at each given participation time in weeks, and then this is like an age-specific mortality curve. So there's an age-specific mortality rate based on that information. So age being how long since you registered to participate in the project. So we see there's very high dropout right at the beginning, and then if people stay in, if they haven't dropped off at this stage, then they often stay in for several more weeks, and then everybody basically drops off when the mosquito season ends. But that means we need to adjust our estimates of sampling efforts. So it's not just a matter of where people were cited with the background tracks, it's a matter of where they were cited and how long it's been since they downloaded the app. So we put together a model of what we're calling propensity to report. So reporting propensity based on how long you participated in the project.
Participation means you haven't deleted the app, or participation means you're saying, oh, I didn't see a mosquito today?
No, so in this case, so the first graph is showing when you delete the app, so how long you actually keep it on your phone. What I'm showing here is whether you're actually sending a report. So your likelihood of sending any report, regardless of whether it's valid, regardless of whether you're reporting a mosquito or a breeding site, what's your likelihood of interacting in some way?
The person who has it on their phone has forgotten. They're not in the picture, the density we just saw a minute ago.
So
They're not, they haven't dropped out. If I've forgotten.
exactly. So the ones who've forgotten are these ones here who stay on and they're being tracked.
How do you tell the difference between someone who is still aware of their app but not seeing mosquitoes and someone who's forgotten about their app?
We don't have a good way of doing that other than through this model. But it's not an ideal way. It would be a lot better, so there's an additional complication, which is we don't actually, we purposefully created separate IDs for the background tracks and for the reports. Because at the last minute when we were about to release the app, we thought, wait a second, we're doing these anonymous background tracks. Everyone's identified by a random UUID. Nobody logs in, nobody has a profile. But if the background track has the same UUID, so a random ID as a report, then we start to have more and more of an ability to link those background tracks with an individual person. And the reports are precise locations. They're not anonymous because we want to know exactly where the people are reporting the mosquito. So what we did was we created two separate IDs. We have the background tracking IDs and the reporting IDs. We can't link those two things together, which makes this part even more guesswork. But this was the best approach that we could come up with, given those constraints. Perhaps there's something else. One thing that we've talked about for the future is some other, so reporting some other information about how, whether they're opening the app, every time they interact in some other way with the app, which we're not currently reporting, perhaps we should get that information.
Is there seasonality in when people download and?
Very much, yes. There's seasonality, and there's also these weird peaks where there'll be a big news item about the project, and then several hundred people will download the app all at once.
Mm-hmm.
Do you have any basic demographic info on the users?
No, we purposely don't collect anything. And of course, that would be really nice, but it was a decision that we made in the beginning. And I think it's a good one because this is sensitive information. I mean, this is not, you can say, right, this is just people reporting mosquitoes, but where mosquitoes are located, if somebody has mosquitoes located in their house. Actually, I was talking to Darrell Cabin, the author of one of the articles from before about this, and he's also done mosquito projects in Hawaii, asking the citizen science approach. And one of the things he tells them is, look, you're not worried about where you're seeing the mosquitoes, but what about if you try to sell your house in a few years and there's a report that there's all these mosquitoes by your house? There's actually things that you may not be thinking about, participants may not be thinking about, that could impact them in a much greater way. But otherwise, I would really like to have that information. So, okay, so our model of reporting propensity, basically, since we don't know anything else about the people, but we can track at least the individual through time, we use a multi-level approach where we have a random intercept for each individual. So basically, we look at a model for given X days after registering the app, what are the log odds that the participant is going to send any report at that time? And we divide this into chunks of 2-week periods. And so we're saying, okay, what are the odds that somebody sends a report in a given 2-week period, X days after they personally download the app? And we put a random intercept for each person on the assumption that there's different intrinsic levels of motivation. So there may be some people who are intrinsically more motivated than others. And so we want to know how much variation is there in terms of individuals with their propensity to report long after downloading the app. So we know there are some people who actually download it and they continue to use it. That's basically the idea. And what we predict from this model is this curve, not looking at the random intercept, so this is just taking the median random intercept and looking at the relationship between participation time and probability of sending a report. It drops off very fast. There's this little bump here, which is probably due to the fact that at this stage, most people who still have the app, or there's more of the people who still have the app are the dedicated users, because the other ones have decided there's not space on their phone. And if you want to look at it with the random intercepts, this is a 3D, so this is a plane showing the range of random intercepts, and the colors here indicate where most of the users are. So the red areas are where the highest density is of the participants with particular intercepts. So,
How does your cubic propensity model behave asymptotically? So these are log odds. Is it well behaved? Is it going to go to 0 as x gets really big? Or is it going to explode in some unpleasant way?
to be honest, I hadn't thought about that.
It might be worth thinking about some other specification.
So I fit this using Monte Carlo Markov chains, using Stan. So I fit this not, I fit it using a completely Bayesian approach. I'm not sure if that then would be affected by the fact of potential weird asymptotic relationships. I don't know. If you have ideas, I'd love to hear them, because if I could improve this model, perhaps I'd give them better predictions. Okay, so given that model of reporting propensity, we then set up a model of simply what's the probability of a valid report of the tiger mosquito being sent from a given sampling cell in a given 2-week period. This is the result of that model. If you want to see the model itself, it's also a multi-level Logan model, also with the third-degree polynomial in it. And in this case, we're using as essentially an offset the sampling effort predicted by the first model. So each cell for a given 2-week period has a sampling effort that's predicted from the reporting propensity model. That sampling effort goes into this model, and based on that, we predict the log odds of a valid tiger mosquito report, or I'm sorry, a reliable tiger mosquito report being sent from a cell. Reliable has to do with where we put the cutoff in terms of the entomologist's certainty as to whether it's a tiger mosquito. And so we get a distribution of basically mosquito risks. Here I've plotted it at the municipality level, even though the model itself is at the smaller scale. But this is for management purposes, it's often more useful to see at the municipality level. And this is the coast of Spain, basically the coast of Catalonia going up, Valencia and Catalonia going up to Barcelona, which is the darkest red area. These are the mean summer, and I've converted this to alert probabilities. September, which is really the peak in eastern Spain. That's when our models, and that's when most people also tell us that the tiger mosquitoes peak.
Can I just, non-technical,
Yeah.
the reason you want to have this model of propensity in the denominator is because you don't think that people are just adopting this randomly over time and space. You
Exactly.
think that in some place you did an event,
Yes.
and then you had a bunch of adopters, so you want to take into account that you have a bunch of implicit adopters in a place?
Exactly. Yeah, I mean, we know that people are not distributed evenly in space, because we can see from just the background tracks, we can see that it basically follows the population distribution in Spain. So people are mostly located in the big cities. But in addition, we're also worried about this effect of the various media announcements, the various workshops, et cetera. This is a model that we're going to have to keep going back and revisiting, because we can't be certain that, this is the model that we fit from 2014 to 2015. It's possible that people's behavior changes over time. It's possible because it may be presented differently in the media, the prevalence of tiger mosquitoes increases. There's lots of reasons to be concerned that this won't hold up over time. But at least it's an approach that we can take in order to try to correct our estimates for it.
Is the thing that you're interested in whether there's this binary thing, is there any tiger mosquitoes in the place or not, or do you care about how many there are?
Yeah, so we do care about how many there are, but we're not confident in our ability to put that directly into a model. So our main concern so we could say how many reports did we get over that 2-week period, but there we're really worried about sort of weird like autocorrelation effects, we have one person who gets very excited and sends a lot of reports. In our models of ovitraps, we also tend to be worried about that. So when you get ovitrap data, you get actually counts of the number of eggs that the entomologist found on the trap. But our approach, and that's been the approach of others that we've worked with, has been to ignore those counts and simply model egg presence, yes or no, during that 2-week period, because there's a lot of concern over, first, whether the counts are accurate, but also so a given mosquito lays a lot of eggs. It's not entirely clear how you would translate that into a model, whether that would give you a good prediction of prevalence itself. We're still treating this as a proxy for prevalence, though, because the probability of getting at least one report should tell us something about the prevalence of type mosquitoes in that area. The other thing that we see it as an advantage of this model is that what this is telling us that ovitraps is not is actually the interaction between the people and the mosquitoes. So, and that's obviously the more relevant question for the epidemiological purposes. But of course, we have these remaining concerns with the model, with the sampling effort. So as a way of validating what we did, we took the ovitraps that you saw in that first map. We took the data from those ovitraps from the exact same time period that we had the citizen science data, and we compared the predictions from both models. Right? So we said, what does citizen science predict about whether we're likely to see a type of mosquito in this particular sampling cell, and what does the ovitrap predict? This is a scatter plot of the predictions. So the probability that's predicted from the mosquito alert models, the citizen science probability here on the x-axis, the probability predicted from the ovitrap model on the y-axis. And then I've color-coded these circles. So the size of the circle is proportionate to sampling efforts. We can see if this sampling effort is throwing things off, and I don't see a pattern there. And then I've colored them according to whether there is actually an egg in the trap or not. So the ovitrap model gives us a probability, but we also know was there in fact an egg in the trap or not. We compare both of those things. So if we look at this in terms of what would we do? How would we use the mosquito alert model to predict the ovitrap presence? It really depends. You could take a lot of different cutoffs. We could just arbitrarily say if the ovitrap model gives us over 50% probability, and the ovitrap model gives over 50% probability, we'll take that as the prediction of positive. But there's no reason that should be the case. That you could arbitrarily set what the cutoff is for the probability for either model. And so what we did as a better and more robust comparison is we used a receiver operating characteristic curve, where the trade-off between specificity and sensitivity that you would get from shifting where that cutoff is shown graphically. A random guess would give you just a straight diagonal line, and anything above that line you're doing better than a random guess. And the two areas, so we compare here the predictions of the mosquito alert model to the predictions of the ovitrap model in green, and the predictions of the mosquito alert model to the actual ovitrap presence or absence of eggs in the blue line. And so the mosquito alert model does quite well in terms of the ROC curve. We can take the best cutoffs that each of those predictions has. We can take the cutoffs where the ROC curve is the greatest, is the farthest from the diagonal, and we can look at the sensitivity and the specificity that we would get from the mosquito alert data. And so in terms of predicting the ovitrap model, we get an 84% sensitivity and a 75% specificity, which I think is pretty good. This is done at the municipality level. We get similar numbers if we do it at the sampling cell level. But keep in mind that there's no data from the ovitraps that's going into the mosquito alert model. So this is entirely the citizen science data predicting the ovitrap results.
Why is the ovitrap a model? I thought you were.
So this is the model from the so the ovitrap
You
data.
also model the
We model it using a very similar model. So this is the model results, and this is the actual egg presence results. We had a lot of discussions about whether we should model it or not, but obviously this is the much more. If you could really predict egg presence itself, that would be incredible. But of course, egg presence and a mosquito biting somebody and then reporting it are two different things. So that makes me quite optimistic about the ability of this approach to give us the information that we would want in order to get a better way of understanding the relationship between mosquitoes and inequality, as well as the general questions of mosquito distribution and how the invasive process is working. One main limitation that we found, though, when we get to this question of the linkage to socioeconomic questions is the size of the sampling cells. So the types of relationships that we're talking about in terms of inequality driving mosquito populations, what I have in mind and what is suggested by the empirical studies of where which neighborhoods mosquitoes are found in is a much smaller scale than what we're getting with these 20 kilometer square sampling cells. So we want to reduce the sampling cells. In fact, we did that with the latest release of the app. We reduced the sampling cell to, I believe, 4 square kilometers now. And the trade-off that we do in order to continue being confident that we're protecting people's privacy is that we're no longer taking the exact timestamp of when the person was sampled. So really all we care about, so in terms of time, we're fine with a 2-week period. We don't need to know the exact hour or minute that the person was in the cell. We're fine just knowing overall there was this many people in that small cell over a 2-week period. And that should protect people's privacy, and perhaps even more than what we're doing with the 20 kilometer square cells and the exact time.
So it's the app itself that's determining the geographic resolution.
Exactly.
It's not post-processing.
Exactly. Nothing exact gets sent to the server in terms of background tracks. So your app processes it on the phone, on your phone. It then determines the sampling cell ID, and it only sends the sampling cell ID back to the server. So that's one part, getting smaller sampling cells so that we can actually link this to more neighborhood measures of inequality, which would be much more interesting. Linking this with more human mobility data. So we've actually taken already the data that we have here at the municipality level, and also a separate study that we did on mosquitoes traveling in cars, which is something that's been long suspected but never previously confirmed. We stopped a whole bunch of cars on the road and we vacuumed for mosquitoes. We, meaning the entomologists, had to do this. And they found 4 mosquitoes, 2 alive, 2 dead tiger mosquitoes in cars after sampling, I think, 700 cars on the road. So there's a very small proportion of cars seem to be carrying tiger mosquitoes, but there's an enormous number of cars on the road. So we see that as a mechanism by which mosquitoes are actually in fact traveling around. So it's not just humans linking the separate subpopulations, but humans linking, not just humans linking them in terms of spreading the disease back to them, but humans linking them by bringing the mosquitoes actually by car to the separate subpopulations. It would be nice to do that at a smaller scale as well, but we don't right now have the human mobility data at that scale. We have mobility data on commuting patterns at the province level from the Spanish active population survey, and we can combine that with our probabilities that a tiger mosquito gets in a car to come up with estimates of tiger mosquito flows between provinces. But it would be much nicer to know this at the scale of municipalities or at the scale of something smaller. And we want to try to have a better link with other socioeconomic data. And that's, so I'm going to give you some very preliminary results on that. That's so far been hampered by the fact that in Spain it appears to be difficult to get good socioeconomic data at the scales that we're interested in. So I was actually surprised that when I started doing this, but the best set of data that I've come up with has been a measure of income inequality at the municipality level, but from 2007. So these are estimates based on tax returns and with some sort of corrections. And so we can get an estimated Gini coefficient for municipalities. So we're doing income inequality and we compare that to the results. This is just a very preliminary look at what I'm finding in the model. So this is a model that compares at the municipality level the mosquito alert probability with the Gini coefficient for that municipality, the mean income, the population density, land cover, particularly artificial services, so how much of that municipality is paved, how much of the municipality has forest cover, and then some interactions between population and those land cover types. So this doesn't tell us a lot in terms of my starting question. This is just a first stab at it using data that's probably too coarse. The estimated coefficient on Gini is negative, but the standard error is very large, and so we really can't rule out whether it's negative. We really can't conclude with any degree of certainty whether it's negative or positive. We do see some interesting effects with the other things. So we see a positive relationship between mean income for the municipality and alert probability, which suggests that perhaps really it's lawn care, water addition, people, watering their plants, more than things like neighborhood disorder. It's possible that that's simply the way things are in general, although that would contradict previous studies that have actually gone through individual neighborhoods, not in Spain, but in other countries, and found this relationship with poverty. It's also possible that there's just not enough neighborhood disorder in the areas that mosquitoes have spread to in Spain, and so the important thing is not trash on the streets, but it's in fact water additions from humans. We also see a very clear positive relationship with the artificial surface. So the more urban areas that you have, the more presence you have of tiger mosquitoes. That makes sense given what we know about this close relationship between mosquitoes and people. It's not that they're seeking out natural habitats where people are seeking out areas where people live, and they're very well adapted to breeding in those areas. And then we see an interesting relationship between population density and artificial surface, where it looks as though perhaps what's best is low-density paved areas. That matches with my anecdotal experience. We've been bitten quite a lot by tiger mosquitoes in exactly those type of low-density paved areas where people often have a backyard, and in the backyard is where you find the water sources. But this is just a very preliminary result from the data that we have. Hopefully, in the near future, we'll have more both mosquito data and maybe more socioeconomic data for Spain, or more mosquito data for other areas we can cross it with. And that brings me to the last step of what we have in mind, which is actually trying to put together a global initiative. As I said in the beginning, what I find exciting about the citizen science approach is that you can scale up. And once you have the app and once you have the system in place, you shouldn't have to have a lot more costs in terms of scaling it up as much as you want. What we have found, though, is there's a constraint in terms of going past the country level, because we do very well in Spain because we have a lot of contacts in Spain. The media in Spain pick it up because we're a Spanish research institute. We have a lot of connections. We've worked very hard to get connections with all the municipal level authorities that are involved here. We have people using and participating in the project in other countries, but much fewer, and we don't have the added value of all those connections. And so we realized, also talking to other people who've been doing these projects, is there's a local aspect that's quite useful in this type of approach. So you can scale up, but you also need to have local players who really know about the particular country, perhaps, or perhaps even at a smaller scale. And so we've been working with the other citizen science focused mosquito projects around the world, with the UN Environmental Program, with the WHO, and with the citizen science associations in Europe, the US, and the growing associations in Africa and Asia, in order to try to put together this global consortium, with the idea of generating a toolkit that then individual projects can put in place themselves. They can put together the toolkits, and they can draw on the tools that we have, and they can get data for a particular country, and then hopefully everybody can pull that together, and we can learn about this issue at the scales that we're interested in, both the large scale, but also the really small scale. So thank you very much. That's where we stand right now with the project and with this research. I'd be delighted to hear any questions you have, or even better suggestions.
Thank you. You actually finished 2 minutes before 1, a record, especially considering how much you told us. So we have 10 minutes for questions. Burka?
I know that your inequality measures are by necessity limited because of your data. And so it seems like right now you're looking at neighborhood level or municipal level poverty. But I was also, as you were talking, I was wondering, it might be really interesting and maybe even possible to find the data to look at within neighborhood level inequality and between neighborhood level inequality, and then especially if you could get gender. Just because I think women are differentially exposed to water, especially if you expand outside of Spain, like if you think about Africa.
Yes, I agree very much so. So I think, part of that is going to be getting the socioeconomic information for neighborhood level, but also part of it is going to be taking this new, starting at the beginning of this past mosquito season and then going forward, the new scales at which we're going to be able to measure sampling.
And then different kinds of inequality within that neighborhood.
Exactly.
Yeah.
And I was focused in talking about this very much on this kind of segregation and in terms of space, in terms of where people are spending their time. One aspect of that is gender-based segregation, where it's not so much different groups in different parts of the city, it's one person spending more time in the household than another, and there's in fact quite a lot of information that could create different exposure levels.
So spatial and temporal level segregation is very interesting.
Yeah.
I'd like to ask about this issue of privacy as the citizen science,
Yeah.
just the constraints that you're putting on yourself
Right.
ethically. When we do something commercial, we get some fine print thing that no one reads, that if you
Right.
want to use the app, you click it.
Right.
And of course, these people are being broken into all the time, our information is being shared. And of course, I understand the gold standard that you're putting on yourself, but, I mean, if you were to ask, if you were to say, offer people the option of saying, can we follow you, can we turn on your, will you turn on your geosensor for us, and you give them large print as opposed to small print? I mean, it seems to me there's a big intermediate space between what people are doing all the time with commercial companies and what scientists like yourself are imposing upon themselves. Is there nothing in between? There are lots of projects like this. Are they all using your approach? Where, and we have this seismic one now at Berkeley. I don't know how that works, but I mean, it's your sensor in your phone, but your geolocation is on.
Right.
You don't have to tell them where you are.
Right. So we've had this conversation, every time we do a new release of the app, I have this conversation. And my main concern is that, yes, you could say it's up to people to decide, but in a way, I'm kind of encouraging it when I'm coming to them as a research group or as a university, and I'm saying, hey, it has the impression of it being safe because I'm telling them this. And the truth is, I don't know if it's safe or if it's in their interest, and I worry that I'm sort of encouraging people to change their privacy expectations by creating a project that does that. But it's a difficult question, and as I said, we keep revisiting it. We finally decided to reduce the size of the sampling cells. We've also had the discussion as to whether we really need to have totally anonymous users, whether probably most people who are participating would like to create their own profile and put their photograph and put their name. And we could very easily have an option where you could do that, or you could maintain your anonymous.
Stepping outside of your project, is the world of citizen science, is everybody kind of doing what you're doing, or is there a wide variety in the privacy protections that are offered to participants?
I think there's a wide variety. I know mainly the mosquito projects. Of the mosquito projects that we've linked up with so far around the world, none of them is measuring sampling effort. So we're actually the only ones measuring sampling effort, and therefore kind of the only ones with that particular privacy question. I mean, there's also a privacy question with just the reports themselves, and that I tend to be less worried about. I figure someone's reporting a mosquito at a particular spot, that's all we know is that there was a mosquito there, and probably most people know that there was a mosquito there. Although that, people may have concerns about that as well.
John?
Thank you, this is totally fascinating, it's delightful. I'm thinking about the problem of people downloading the app, using it for a day,
Right.
and then forgetting about it, or with 38,000 ever users and 11,000 reports, a lot of people
Yes.
download it, they don't see any mosquitoes, they get bored, they forget about it.
Absolutely.
And thinking then about your last point about expanding, and wondering about expanding by allowing people to report a wider variety of things, that people might download, they might forget about the app or
Right.
not care because after a while they just don't see any tiger mosquitoes.
Right.
But they might see other species that might be of interest,
Yes.
either as vectors
So-
or for other for other
Right.
reasons. Maybe that would keep people more engaged with the app.
Yes, I think that's a very good point. In fact, we've done, so I didn't mention this, but there's two other aspects, and they both go to that question. So from the beginning, we also allowed people to report breeding sites. First, because we thought that was useful information, but also because that was really nice for doing workshops in the wintertime when there's no mosquitoes in Spain, but you need people to go out and look for something. So one thing people can do is they can report breeding sites, but almost nobody reported breeding sites. They found it very boring. I like to report out breeding sites. So the other thing that we just added to the last release is the ability for people to actually validate each other's photos. So we still have the entomologists doing the expert validation, but we also have this crowd validation approach. And we had previously done, we actually haven't used the crowd validation so far in our analysis, but we had previously used a crowd platform online where people not connected to the app could go online and do that. And what we realized was, let's put that in the app so that people have something to do that's actually fun and they get points for it.
Yeah.
So you get points, you get a silver and a bronze for some reason still, which is not fair. And for that validation, 30 people agree. So you take the results of 30 different people viewing one particular photo. But there may be other things we could be doing in that regard to continue getting people interested or maintaining their interest. And also other things we could do to track. So right now we're not tracking how much they do that. Whereas if we would track that, that would be a great sampling effort.
We have Mike and then Ron.
I was wondering if you could expand a bit on this problem of whether we can use this approach to actually get estimates of numbers. Because I guess the situation in Spain, you want to know if this mosquito is there or not.
Right.
But in a lot of places in the world, we know it's there. What we want to know is
Yeah.
where the numbers are going.
No, and in Spain, we really want to know the numbers too.
Yeah. So presumably you need it to be a bit more active in some way, or you need
So-
to turn it into a game. I was wondering if you'd have thoughts about it.
Yeah, so I mean, I guess with more data, you can be more confident, but I would still rely on this more robust approach of sort of presence, absence, and report in a given period of time. What I would really like is to get some population, some actual better gold standard for the population density in particular areas to compare that to, and maybe come up with a way of adjusting this alert probability to an actual population density. And I guess the gold standard for that would be these actual traps, so the adult mosquito traps, not the egg traps, but they're these traps that adult mosquitoes fly into. You can do release and marking mosquitoes. And we actually have a project, the entomologists that I'm working with have a project lined up to do some of that. Hopefully they're going to do it this fall, but there's been constraints in terms of what permission they could get from the authorities to release mosquitoes. So what they're going to get will be better than anything we have so far, but it's not going to be as good as it could be if they actually release, mark and release large numbers and capture them.
Or the users could throw Pokeballs and mosquitoes.
Yeah, it was Pokemon mosquitoes.
Yeah.
What's that?
Pokemon
mosquitoes.
Yeah.
So I have two short questions, thoughts, and then something a little longer. I want to have the phones ping every month or something and say, have you seen a mosquito in the last 2 days?
Yeah.
That was the first.
Right.
You can just leave any of these. Second, you said seasonality was important. I didn't see seasonality in your model.
Well, you know what? Thank you, because I forgot to show you the coolest chart. So, oh, that's right, I forgot, it's not on here. So here is seasonality. So this is, so we take the model and we do predictions by day. And this is an animation going through the mosquito season. You can see where we are in the season here. We're now getting to July of the municipality level predictions.
Okay.
What are you using?
So it peaks, pardon?
What software are you using?
So I just, in R, I simply did the predictions, created a map, and then put them all together as a GIF using something to link them together.
So you do have seasonality in the model.
So we have seasonality in the model, and we actually have it as random slopes on the assumption, particularly as the process expands across Spain, the seasonality will be different in different places. And I'll show you when I get back to you.
Yeah.
Okay, so we have time for your big question, Ron, and then we have to bring it to an end. Do you want to do your big question?
Well, yeah, it's not that big, but the this is related to what Bo was saying. I mean, I can see why you use the Gini, because the Gini in relation to this stuff is relevant for your metapopulation story.
Sort of, but not spatial.
Sort of.
Yeah.
But the neighborhood seems to me having measures of small area socioeconomic status seems very relevant for looking at the causality in that other direction and so on.
I completely agree.
But then to do that and to use it that way, you would have to have some sort of serious study of propensity to report, to own a phone, to report, to participate, and so on by socioeconomic status or something along those lines. Because otherwise you won't know.
Although my assumption is all of this is spatially organized. And so if we would have good data for the US, for instance, where we have much better neighborhood level socioeconomic data to compare it to, I would be fine with using the sampling effort data so we could see if somebody's going to a particular neighborhood and sample, or if somebody using the app has been in a particular neighborhood. In a way, we could get an estimate of how likely people are given their neighborhood, and maybe even from that as a proxy for socioeconomic status. In general, I mean, studies from other citizen science projects in general have shown that it's hard to get people with less resources to participate in citizen science. But there's some projects have been successful by adopting sort of like an environmental justice approach, where you go to places that are really being hit badly by mosquitoes and say, look, this doesn't take a lot of time, it's interesting, and you can help to make your life better.
Can't you access the public use microsample from the census to get your SES data
Yes.
however you want it?
Yes, the problem is that I don't have good mosquito data for the US. I mean, we have some people participating, we have, you see those cells lighted up in the US, but we don't have enough reports in the US. So hopefully if we can get a group in the US to implement this and we can get good data, that would be useful.
Okay, thank you so much for great
Thank you very much.